Well, thanks for the generous introduction. It's not easy to actually give a talk after the two amazing talks by Joshua and Trevor, and then before lunch. So let's see if I can do it really well. And as Joshua talked about earlier, these neural net-based language model or the machine translation systems have been extremely successful. Google Translate that you use already has been using this system since 2016. Microsoft uses it, Facebook uses it, Amazon provides the translation API for you to actually try it out right away. And then Systrom, which is one of the oldest machine translation company, uses it. Even the patent office in Europe uses this system to translate the patents automatically across all those European languages. And if you use Booking.com to book a hotel, then you may have actually seen some of the reviews that were automatically translated. And a lot of the users don't even realize that they were automatically translated. And one of the core engine behind this sequence-to-sequence learning or the machine translation system these days is so-called unbounded autoregressive model. The goal here is to try to build a system that is able to assign a probability score to each sequence. And then in doing so, this model is going to make an assumption that the sequence was created one word at a time from left to right or right to left. And then the score of the sequence is going to be simply a product of the score of predicting the next word in this sequence. And then there are two things that have been implicitly assumed here. First is that if we're trying to model a distribution over complete sequences, that is, we want our model to see a complete sequence and then trying to give a single score to the sequence. And the second thing is that all these sequences were somehow created in background, one token at a time, in a monotonic fixed order. And then the question here is that can we actually go beyond this paradigm and then try something more fun? So instead of looking at this as a modeling the complete sequences, we decided to look at this whole process as modeling the process of sequence generation. If you think about any kind of sequence, it doesn't really have to be written left to right, especially when you write. You, in fact, go back and forth as you write a sentence. So what we're going to say is that a sequence is the result of the process of generation where we apply the little by little revision or the edits. So just as a random example, we can start from some empty sentence. So we're going to have all those empty placeholders. We're going to replace the first word, and then we're going to replace maybe the third word. Maybe we're going to replace multiple words at the same time until we are satisfied with the completed sequence. And then what it means is that we can now put a probabilistic model on top of this generation process itself. And then if I had to make one, then how would it look like? So I'm going to have a length distribution because I need to decide on the length of the sequence. And then at each time step or each process of the refinement, I need to decide which words or which location I'm going to replace. And then given that selected location, I need to decide which symbol with which I'm going to replace the original symbol with. So I need these three elements. And then once I define these three elements, suddenly I have a model that is very different from what we are using at the moment, in a sense that it models the generation process itself. Once we have this kind of model of the generation process, we can, of course, recover the distribution over the complete sequences as well by marginalizing out all possible ways in which a given sequence could be generated. Of course, that looks like a pretty difficult thing to do because there are so many ways in which we can generate a single sequence. So we're going to kind of forget about it. And then say that, OK, we can do it if we wanted to, but I don't think we want to. And then it turned out that although it's a pretty new way to look into the sequence generation models, it is one of the standard approaches to density modeling in machine learning. So denoising autoencoder is one particular approach in which we are learning the generation process that goes from some random configuration in the input toward a highly likely configuration. And then even PCA, depending on how you write it down, you're going to see that it actually does reflect the process of generation, just like in denoising autoencoders. And this traditional, or more like the modern-day unbounded autoregressive model is also a special case of this framework in a sense that it starts from, let's say, empty sequence. So it's going to be filled up with all those empty tokens. And then we always select the next word to be replaced, and then the replacement is going to be decided based on all the previous tokens. So it's a very degenerate, uninteresting case, but we can see that this framework actually allows us to see a larger picture and then trying to be more creative in terms of building a sequence generation model. So today I'm going to, if time permits, go through the 3 different approaches that I've been looking into in recent years. First one is parallel decoding. So once we start looking at this problem of the sequence generation from modeling the process of generation itself, then we can start asking questions such as, does generation have to be sequential? Perhaps what we can do is we can try to generate the entire sentence simultaneously. But then if you think about it one step, then you realize that, it's actually not possible. Because the fact that we're going to generate everything simultaneously in one step implies that we're going to ignore any of the dependencies among the words in the target given the source. So we're assuming a very strong conditional independence assumption. And as you can guess, the language or the sentence is full of very strong dependencies that must be captured. And then that connects to what Yashua earlier said about the vanishing gradient issues and then trying to capture the long-term dependencies. However, what we can do is we can use this one-step generation as one single step in this full sequence generation process. And then if we assume that we have enough parallel computational resource, and then the number of steps that is needed for this system to generate a translation is going to be less than linear with respect to the length of the sequence, then suddenly we can build a very efficient translation system that can go much further in terms of efficiency than the sequential generation model. So for parallel decoding, what we decided to do was, we're going to replace every single token in the sentence every time. But then when we replace each of those tokens, the network or the neural net is going to look at the entire sequence, not only to the ones on the left or to the right, but on the both sides. And then this is how this model is going to capture all those strong dependencies in the translation. And for the length distribution, we simply use the maximum likelihood estimation, or we build a classifier, in other words, to predict what the length should be. So this is going to be, let's say, one figure that I'm going to show as a kind of neural net length thing. However, the interesting thing about this whole framework is that it's about how we build a probabilistic framework for solving this problem, and how to parameterize each of the distribution is largely an orthogonal issue. Of course, we want to use a very powerful neural network because this parameterization actually does matter. So in our case, we've been using the transformers, so based on the self-attention, that first encodes the source sentence or image. It could be very agnostic to that. And then try to predict the distribution over length. So that's going to be f length. And then given that, we have the decoding neural network or the transformer that's going to look not only at the source, but also at the intermediate sequence or the translation that is going to refine by one step. So once we have this probabilistic framework, parameterization, now we need to decide on how we are going to do learning. It turned out that the whole process of the parallel decoding or the parallel generation is equivalent to denoising or iteratively denoising. So you can think of it as you start from some random translation given the source sentence, and then we want this neural net to denoise it little by little until we end up with a very clean sentence that is a translation of the source sentence. And already in 2014 and even before, in University of Montreal, Yoshua Benjo and his colleagues showed that this is one way to learn the distribution itself. That is by learning the gradient field in the input distribution. And what we can do is we can now use this idea to train this model end-to-end. The first thing we had to do is that to verify that it actually works. So a lot of the nice theory about denoising autoencoders and so on are based on the continuous random variables. On the other hand, here we have a very high-dimensional discrete random variable, or even a sequence of random variables. So we tried it on various tasks with the various sizes, and then what we have shown first is that indeed this theory works, and then we can train this model to do the denoising, and then we apply it over and over in the test time to refine the translation to get better and better. And then we push it to the extreme by refining up to 100 steps in the test time after training model with only 4 steps of the refinement. And then what we saw was that the performance only gets better and better, and it never really gets worse. And furthermore, what we have seen is that the convergence of this refinement process indeed does take only the logarithmic number of steps with respect to the source sentence, giving us a hope that there is really a possibility that we can build a much more efficient translation system in the future. Let's look at a couple of the examples. So this is the example of a system that translates from German to English. The English reference translation is not, let's say, as faithful translation as possible of the source German, but bear with me. Anyway, I don't speak German, so who knows, right? So the very first translation does look somewhat like a translation. It does have many of substances, but it's not really well formed at all. But as we let the model refine it further and further, it's going to put in more substances, remove any of the unnecessary contents, and then form the syntax in a way that makes it a perfect translation of the original sentence. And then these are not really cherry-picked examples because this is precisely how we train these models to do. This is what we get for any of the any of the sentences that we take. And then we could see a similar thing with the image captioning as well, where the input was an image of a bus parked in a parking lot. And then initial caption does have most of the substances that need to be described, however, just not in a well-formed manner. As we let the model refine it, what we see is that it both refines the content as well as the form of the sentence. However, as you may have guessed now, does it actually work as well as the state-of-the-art systems? It was, until last year, it was not true, and then still it's not true, although the gap is narrowing. And then after presenting this work at 2018, last year at the EMNLP, we started to look into, okay, what is the issue here? How can we make this work better in terms of machine translation or some kind of sentence generation? And then one particular weakness that we have found was that each iteration, so each symbol replacement is just statistically very weak because we still make that conditional independence assumption. And then what we want is that we still want to introduce a way for a model to capture a bit of dependence every time it refines. Not as much as the autoregressive model, because that's going to defeat the whole purpose, but just a little bit so that the model can make a better decision or the larger refinement at a time. So what we did was to replace this very weak conditionally independent replacement distribution with the latent variable model, in particular variation autoencoder with a very low dimensional continuous latent variables. And then in this variation autoencoder, we can use a very clever parameterization to maximize not the actual marginalized low probability, but the evidence lower bound. And then to do so, we introduce 3 different networks. Now we have 3 different networks. One is that the usual generating network that's going to take as the input the source and the length and the latent variable configuration, and then generates translation. And then we have the prior network that's going to look at only the source and then trying to determine what the good latent configuration should be. And then finally, we have a proximal posterior network that, had I been given a correct translation, what would have been the correct latent variable configuration? And then everything is end-to-end trainable, and then we train a model on a large enough data set. Now, the interesting thing is that the training variation autoencoder is relatively straightforward nowadays. However, inference or the generation from the variation autoencoder, the conditional variation autoencoder, is a very difficult problem, because how are we going to actually figure out what is the correct solution? This is one of the most difficult combinatorial optimization problems you can think of, because the length changes, the dimension is gigantic, and then computing the score of each of the configuration of the sentence is very expensive. So we came up with a very simple EM-like procedure that allows us to to generate deterministically the solution from this variation autoencoder type of network. And it turned out this procedure itself corresponds exactly to the denoising or the refinement-based sequence generation. So we're going to first generate the latent variable configuration, and then based off which we get the first initial translation. And then given the initial translation, we're going to refine the latent variable configuration, based off which we're going to get the next refined translation, and then we go back and forth until it converges. So we implemented all these things, trained a model on the same data set that we had used last year. And then what we see is that now the gap between the state-of-the-art autoregressive baseline and this parallel decoding model is substantially narrower than before. And then the surprising thing is that the efficiency in terms of how many sentences or the words could be translated every second on average has improved as well. That's surprising because we now have 3 times more networks that we need to run every time, and somehow it's faster in terms of the wall clock time using the GPU, and then we optimized everything that we could. The reason being because we gave more power to each iteration of refinement. Now we can converge or refine the sentences in a much fewer steps, which lead to the decrease in the wall clock time to translate each of the sentences. And then we could see this for not only for English to German, but also for Japanese to English as well, verifying that this approach is a very generic approach that can be applied to different language pairs as well as different modalities as well. Now, while this was happening, late last year, something big really happened. And then we already heard about it in the very early morning in the opening keynote as well, is that the BERT happened. So everyone in natural language processing was going into BERT and then trying to use the BERT for this and that, and mostly for transfer learning. That is, they use this BERT that is a very large language model to initialize their downstream classifier and then got their classifier to work well even with a small amount of data. However, as a sequence generation person, what I wanted to see was what this BERT as a language model could do. And then if you think about what BERT is really nothing but a very particular type of the denoising autoencoder for natural language sentences. You take a sentence from your data set, and then you're going to randomly mask out a few of the tokens, and then replace those masked out tokens with either special mask token, or keep it as they are, or you're going to replace it with some random tokens from the vocabulary. And then this corrupted sentence goes into a transformer, and this transformer is going to be trained to fill in or to correctly predict what those masked out tokens should be. And then that's, by definition, a denoising autoencoder. What it means is that it actually learns a distribution of the sentences. And then if it does learn the probabilistic distribution of sentences, we should be able to either sample or find the sentence that has a very high probability under this model. And another perspective that was put forward recently by David McAllister in his blog is that the BERT is a way to learn a density model, a density or the distribution in a very convoluted way. That is, if you think about what we do in order to learn a distribution, we're going to either build a gigantic table, which as we learned earlier in the morning, that cannot be done really easily, or what we do is that we're going to look at a set of conditional distributions induced from this joint distribution and then trying to match all of them. In the case of the autoregressive model, it was the conditional distributions that correspond to predicting the next token. But it doesn't have to be like that. You can just have a set of many conditional distributions. And then in this case of the BERT, it's going to try to match every possible one of them as well as possible. So what we did was to use this BERT, or the cross-lingual BERT that was pre-trained by the Guillaume Lempo and Alexis Kono from Facebook AI Research Paris, and then take it as it is, and then we're going to use this system to generate or to make a translation out of it. And then the big question is, how do we decide which symbol to replace at each time step? That is a big question because that, in fact, is equivalent to figuring out the dependency structures underlying each of the sentences separately. So I have to confess something. So far, I've been always saying that you shouldn't really use a linear model because who knows whether your problem is linear or not. You should never manually craft the features. You gotta learn them because you probably don't know what you're doing, and then you need to learn everything end to end. However, in this paper, because we wanted some proof of concept, we used the log linear model with the handcrafted features, and then even the coefficients we manually set in order to induce a very specific properties from these coordinate selection distributions. However, what it means is that there is a large room for improvement by learning this whole thing together. And then by doing so, we created 4 different types of coordinate selection strategies. One is just very dumb uniform strategy. Second one is the left to right. So we're going to use BERT in a way that we would have done with the autoregressive model. And then there's the least to most easy first, both of which are based on what the distribution or the conditional probabilities BERT is going to compute. And then the interesting thing is that the all these strategies, like the third and fourth ones, induce a particular pattern of generation across different examples. And then all those examples have a different order of generation. So the plot that you're seeing on the bottom of the slide corresponds to showing the clusters, so the representative examples of the order of generation of the translation. And then what we see is that it's never just one order that is applied across all the source sentences. Sometimes it's going to generate from right to left. Sometimes it's going to generate right and then all the way to the left and then filling in the middle. And then it's going to be very dependent on the source sentence. So let's look at one example. So again, this is German to English translation. And then what this system does, or what our, let's say, framework does, is that the first is going to fill up the very final token. And then BERT is going to tell us that, that token should be question mark. And then asks for it. And it jumps all the way back to the beginning and then puts the would I ever, and then goes into the middle and then fills up some of the information and then eventually builds a complete sentence or the translation that I think is probably better than the reference translation that we have there of the source German sentence. And then this actually did narrow down the gap between the autoregressive model and this kind of non-conventional, let's say, sequence generation model quite substantially. And then what this kind of approach allows us to do is to build a sequence generation system that learns not only to just complete a sentence once, but learns to complete it and then refine it further. And what I believe is that this is in fact the key to applying the reinforcement learning or the policy gradient to the sequence generation, because then now the policy can make a mistake and still recover from its own mistake. And then furthermore, what we see is that there is a high variance in terms of the BLUE score across different decoding strategies, which does suggest that we have a large room for improvement if we start training everything from scratch. And there is a very interesting, let's say, consequence from having this kind of BERT-based model with the coordinate selection distribution that we design, is that we can now do the constant time translation. That is, if you have enough parallel cores that we can use, that the number of the cores has to be longer than the, let's say, source sentence, what we can now do is we're going to say, here's a particular budget that we're going to allow, and then this whole framework needs to generate the translation under that computational budget. Now, what we do see that they actually do the job pretty well. And then the gap between having a fixed budget that is, let's say, 10 here, that means that the 10 steps of the refinement, which is going to be only about 40% of the average number of the words that you would expect from the translation in this particular data set, the gap is only about 1 or 2 BLUE scores, which means that in a very resource constraints in terms of the computational budget setups, this approach could be very much viable. So this is what the BERT happened, and it turned out the BERT is an amazing generation model. But then you realize that, so BERT was trained offline, and then I took the coordinate selection distribution myself and then designed it myself. Now, can I actually build a whole system that is trained end-to-end from scratch to learn to generate in an order that is going to be adaptive to the actual content of the generated sequence? And that's where we run into the so-called non-monotonic sequential generation. And then when you think about building any kind of structured object or building any algorithm that is going to generate a complicated structured object, the question that must be answered is, given a partial completion of the structure, what should be generated next and where? And then once you can answer this question, you can apply this answer over and over recursively in order to build a very complicated or the complex structure out of it. And in the case of the sentence generation or the sequence generation, a typical example would be we have a partially completed sentence, let's say the and then empty, set, empty, 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 and period. And then if I knew what the target should be, then I can precisely tell what are the possible next steps that we must take. So the first one is going to be to put the cat in front of the set, or the other, the second, third, and fourth options correspond to putting either on the mat to the right of the set, but before the period. So once we can answer this question, then we can generate whatever the complicated structure, including sentences as well as the general graphs, as you want. Oh, so this work was well, like Brantley, Dome, and me. Okay, so it's been cut off, but it was presented at ICML earlier this year. And then now the question is, how do we actually build a generic algorithm that allows us to, or that tells us what are those possible next steps in any kind of situation? There are, of course, many different ways to do so, but one direction that we have pursued was to be inspired by Quicksort. I believe that there are many students here, and then I believe some of them are computer science students. However, how well do you remember Quicksort is implemented, the algorithm? We all remember that, like import numpy, numpy.sort. By default, it's going to use Quicksort, and on average, it's going to have the n log n complexity. But how does it do that, right? But it turned out that it's very useful to know about this in order to build this kind of model. So let's see what I mean by the inspired by Quicksort. Let's say my target sentence is the cat sat on the mat, period. Now, how can I generate this sentence is that initially, I'm going to start by some, let's say, shuffled words, and then I pick one word. Let's say I pick the on. And then given that on, this on acts as a pivot element in this sequence, and then I can divide this sentence into two parts. So one part contains all the words that lie on the left side of the on, and then the other side is going to be all the words that lie on the right side of the on. And then now I can apply this procedure recursively, building a binary tree. And then let's see what was the order of generation. This whole sequence was generated generated by saying on, set, mat, cat, the, period, the, and then stop, those special tokens. However, once we have built this binary tree, we can now follow the so-called in-order traversal to collect all these words in an order that's going to preserve or that's going to match perfectly the original target order that we wanted. And then this is, in fact, how the Quicksort works. Now, how does this plug into this learning a non-monotonic sequential generation model? So we're going to have, as usual, a neural network G that's going to take as the input some arbitrary input. Could be the source sentence as well as images. It doesn't really matter. And then our decoder is going to start generating one token at a time. Let's say it generated on in the first step. Then, based on this, we can start building this binary tree. And it generated set. And then now we want to figure out what should be generated or what could be generated in the third step of this whole generation process. And then thanks to the availability of this binary tree or the Quicksort-like procedure, we know precisely that it has to be any one of the mat, period, or the, and then nothing other than that could be predicted. And based on this, we can build now a so-called oracle distribution or the target distribution that's going to have probability, non-zero probability mass on mat, period, or the. And then we can now minimize the divergence between what has been predicted that is given by this neural network and then this oracle distribution. And this is just simply supervised learning. Although we've heard a lot about the limitation of the supervised learning, but supervised learning is the one that we know how to make work. So what we can do is, what we have done here is to reduce the very complicated problem of figuring out the order of generation simultaneously with what to generate into a series of the supervised learning problems. And then now we can train this model. And in the imitation learning world, if you're familiar with it, we are often going to call the process of generating up to certain time step as a roll-in, and then the process of computing the oracle distribution and then trying to get the learning signal for this neural network a rollout. So how does it fit with the non-monotonic sequential generation? How does non-monotonic sequential generation fit with the framework that I told you about? It turned out if you write it down in a very convoluted way that you definitely don't want to do and then have to do, in fact, this level set traversal inspired by the Quicksort corresponds to coordinate selection, while symbol replacement is simply done by the autoregressive model that traverses along the generation process of this binary tree. And the length distribution is implicitly defined based on how many stop nodes have been predicted. Now, it was, when was it? No, October last year that we got all these algorithms all together and then started implementing it and then running, about to start our experiments. And then it was pretty radically different idea from our earlier work. So we were like, okay, so we need to do it, tried it on a toy task. And then the toy task was to train a model in an unconditional generation mode. So there is no input. And then we trained this on a set of utterances from a very simple dialogue data sets. Now, one nice thing about this model is that it can generate a sequence in a very arbitrary order. But one very significant weakness is that it's an implicit probabilistic model, and then we actually don't know how to compute the probability or the well-normalized probability of a sentence given this model. Because we have to now marginalize over all possible ways in which the sentence was generated, and then there are exponential number of them. So what we did was to train a model and then simply generate a lot of sentences and then looked at how they look like. Now, the numbers here are pretty meaningless because we created all these measures ourselves in order to satisfy the reviewers of the ICML. However, it was very informative to look at how the model generates a sentence or the utterance. So I'm going to show you one particular example. And then this one was just generated out of box by a trained model. So it puts a period first, and it's going to put you, and then another period, I, study, I, and then stop. So stop means that we're not going to expand on that side of the subtree anymore. And then stop, wish, could, LOL, stop, A, stop, 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 and then work lot, stop, 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 stop. Now, the generation was pretty weird. It's difficult to tell what was generated. However, if we follow the in-order traversal and then collect all these words, then what we see is that it's a pretty reasonable utterance that you see from usual conversations. That is, I wish you could study, LOL, period. I work a lot, period. And then what we did was that looking at these kind of examples, what we wanted to see was, okay, what kind of structure has it captured? So if we compare the third one, if you look at the third one, that is what we proposed, what it does is that initially, in the early stage of the tree, it's going to put the punctuation first, and then put the pronouns, often which are subjects of the sentence, and then put verbs, and only at the very end is going to put all those nouns that are often objects of the subject work doing something, that is the verb. On the other hand, if you look at the left-right generation, simply looking at the left-right on the left side of this slide, it's almost always a pronoun. So we're looking at English here because that's subject, and then it's going to put the verb, and then all the nouns follow, and then there's going to be a punctuation at the very end. Now, comparing these, looking at these two, and then compare it to what you get from the dependency parse. So that is one of the shallow syntactic structure you can get from the natural linguistics. We do see a pretty good resemblance between what we propose and the dependency parse. That is, often the verbs are going to be predicted earlier than nouns. And then the pronouns and verbs come together often. Now, what it means is that somehow this approach that we trained without any, let's say, bias or the knowledge that we have injected using the linguistics has learned this kind of interesting linguistic structure that we might find, or at least the linguists might find interesting. And furthermore, what we see is that the easy first behavior emerges. That is, when you try to generate something, what often happens is that you have a very high uncertainty, that is the high entropy at the beginning, and as you generate, you're going to collect more and more evidence, and then you're going to end up with a very low entropy. So at the end, you only have one or two options from which you can choose. However, our approach does something the opposite. It's going to start by putting things that it's very certain about, that has a very low entropy, but then it's going to, and then based on those, let's say, highly predictable things, it's going to move on to highly unpredictable, let's say, tokens. And then, of course, it doesn't monotonically increase only, the green curve shows, because it also accumulates the evidence as well. So there is an interesting balance of the trying to predict the easier one first, and also trying to collect the evidence as much as it can. So we tried on machine translation. Unfortunately, it didn't really work well. But one thing that we have noticed was that how the gap between the state-of-the-art oral regressive model and this kind of non-monotonic sequential generation models change based on what kind of automatic quality metrics we use. So the difference in the blue score was pretty gigantic, almost, let's say, 6 blue scores. However, when we look at Rive's score that actually takes into account the dependency structure or the parse, then the difference actually narrows down quite significantly, which means that all these different models have a very different properties when it comes to how they generate things and then how they actually work computationally as well as statistically. And then perhaps what we need to do is start looking at all these different algorithms and then trying to figure out what are the best use cases for each one of them. So if you look at just one example here, source was German, and then the target was English. And then what we do see almost always is that it's always going to group, this approach is going to group all these sub-phrases into subtrees. So it'll never divide a phrase across multiple subtrees. And then this is really interesting because we never actually told this model or the learning algorithm to do so. It just found this solution because this was the best way to do so in order to maximize the learning objective function based on the data. And then, of course, the very interesting thing is that when we were working on this, there were 3 other groups in the world who were working on almost exactly same problem. So at Facebook AI Research, so I was involved in part of this work as well. Jiatao Gu and others have come up with the idea of the insertion-based autoregressive generation, where they model this order of generation as a latent variable, and then where they approximately marginalize them out. And then at the same time, Mitchell Stern and others from Google Brain came up with the idea called insertion transformer, which in my opinion, is the best of the both worlds. So they use the imitation learning really well and also use the transformer in a way that just fits this application perfectly. And then without anybody knowing, Google DeepMind in London, together with Yoon Kim, who was an intern back then in the Chris Dyer's group in DeepMind, came up with the idea that was much more rooted, directly rooted in the linguistics or the syntactic theory, that is, trying to come up with a neural net that is going to follow or can capture the constituency parts perfectly, and then assume that that rules are actually not given. Then can we figure out how to, which set of rules are necessary in order to get those sentences? And then Yoon Kim was able to somehow make it work, while let's say the previous, let's say, several decades, no one has been able to make it work. So that was pretty amazing. And furthermore, the thing that I've been getting into, although I've been talking about the sequence generation, falls more in a broader category of learning the structure of a data or the individual instances over which computation is done. So often when we think about extracting the structure, we think about it as, okay, we want to extract a structure, and then often done. However, what we are now seeing is that you want to extract the structure and then design the computation or the information flow along the structure in order to solve the problem as well as possible. And then this idea, of course, goes back all the way to, let's say, 80s and 90s. And then various names have been used, mixture of experts, dynamic routing, and sparse latent structures, dynamic computation graph. But all these studies are pointing into the one direction, that is, that in order to solve a complicated problem, we need to solve all of them all together. However, we also have to learn the underlying structures that are going to be exploited for computation itself. And then the figure on the right side in this slide, I just took it away from the Jeff Dean's keynote speech at ICML this year. And then this is one of my favorite figures. I think that is the right way to go. That is, it's not only about modeling the data itself, but we need to model the structure of the computation and flow of the information so that eventually we can build one system that can solve as many problems as possible without having to sacrifice our computational efficiency. So nearing the end of my talk, so I talked about so at the end of the day, it's very much of the details that I have talked about, is that there are 4 types of the neural sequence models. And then first one, the autoregressive neural sequence model that uses a monotonic fixed generation order. That is the one that is state-of-the-art, is used everywhere, and then is probably running at the moment on your smartphones. and then probably listening to you as well, as you say, or the listening to me at least. But at the same time, there are many different alternatives. And then I talked about the parallel decoding approach that is effectively the denoising autoencoder. And then I talked about the masked neural language model. That's how to generate from birth. And then finally, I talked about how we can use the idea from the imitation learning to build a system that learns not only what to predict, but also where to put the predicted token automatically from scratch. So to wrap up, it turned out that these alternatives that naturally fall off of this general framework of trying to model the generation process, not only the completed sequences, are catching up pretty quickly and then seems to have a very interesting areas in which they can work better than the monotonic sequential generation. And then it was really nice for me to think about this whole generalized framework because that allowed me to look at what are the missing pieces or what are the missing combinations, and then also allowed me to rapidly check together with my PhD students on if this BERT is capturing all those knowledges, then can we use that to generate as well? And then this one was really like the 2-month-long effort that worked out pretty decently, let's say, because it was rejected earlier and is still under review. And then my question is that in this extracting deeper structure from data automatically and then using that structure for computation, what else can we think of? And then what is the right next step to explore? Perhaps I can end my presentation with this question to all of you as well. And thank you very much. Yes.